Yes, the last lesson of AP Calculus AB, last new content. Certainly not the last lesson. I'll be doing lots and lots of review between spring break, after spring break and exams, which is, I don't know what it is this year, sometime in the beginning of May, 13, 14, something like that. We are learning how to find volumes of solids. So to do this, I love this lesson. I got really good lessons already online. But, you know, every year I'm trying to adjust how I teach this a little bit because you have to have a good, maybe not such a great ability to see in 3 space. You don't really need to understand what the overall shape of the solid is that you are about to find the volume of. But you do need to have a good ability that we started to review in 7.1 of being able to draw functions, sketch them just well enough that you can see, you know, which function is farther away from, well, in this case, it's going to be the axis of rotation or another function. Like basically, we found areas of curves. We wanted to make sure that area was equal to a positive number. So if we were integrating with respect to x, where we had representative rectangles that were generally long, thin rectangles with a lot of delta x's, then we needed to do big Y minus little y. If we had a problem that was going to be easier to integrate along the y-axis and we had horizontal representative rectangles giving us a bunch of delta y's, then we wanted to take the function first that was giving us the large value of x, the one that's on the right side, and subtract it with the function that's on the left. So we're going to start this little journey with not jumping right into calculus, but remembering what you did in geometry. So how do you find the volume of a prism? And a prism is not just the thing that takes light and bends it into a rainbow. It's just a solid where the 2 bases are the same shape with the same size. So we might be finding the volume of a cylinder. The volume of this cylinder is what? How do you find the volume of a cylinder? The volume is equal to the area of the base times the height. Okay, so in this particular problem, we're going to have a base which has a radius of 2 and a height of, let's say, 9 units. So r is going to be equal to 2. The height is going to be equal to 9. And this volume is going to be found by doing pi times the constant radius of 2 squared, multiply that by the height of 9, and we get pi times 4 times 9, or 36 pi cubic units. And that's how you find the volume. Easy peasy. Maybe we'll step it up a little bit. Maybe we'll give a prism that has a, yeah, let's do this first. Instead of a prism, let's talk about a cone. How about a cone that also has a height equal to 9, that also has a, that's not quite in the center, but also has a radius of 2. How are we going to find the volume of that cone? Somebody else. And we haven't done solids and geometry for a very long time, so I'm not sure if anyone's going to remember. But anybody remember how to find the volume of a cone? It's something with a third, though. So it's 1/3 pi r squared times the height. Got it. And Sophia was close. If you want to find the volume of the sphere, which is going, cone, excuse me, yes, it's early in the morning, and if I may say something silly, just maybe, yeah, laughing at me is okay. Give me a little heads up that I said something dumb. This volume is going to be 1/3 pi r squared times the height. Now I'm going to leave this example in blue because we're going to find the volume of this cone another way here in a few minutes. But the formula that I'm writing out right now is not really necessarily something directly correlated to today, because we are learning calculus. This is, again, the last section of at least College Board's curriculum, AP Calculus AB. We're finishing what we would call then, Calculus 1. So this is going to be 1/3 pi. Our radius is going to be equal to 2, so we have 2 squared. And our height is going to be equal to 9. And that means that we're going to have 9 divided by 3 is, of course, 3 times 4 should be, 12. Oh, just trust yourself. My brain's half awake. I'm not trusting myself. I should just do that. 9 divided by 3 is 3 times 4 is going to be 12 pi units cubed. Okay, so I thought this way I'm teaching this lesson is going to be a little bit of a variation. I'm constantly changing this lesson because, again, I'm able to see it really clearly, but not all of my students, not all of you, learning this for the first time really catches on to volumes of solids initially. I always think the lessons come out super great, and then sometimes some students struggle. So I'm going to, this year, try and teach this lesson with a tie-in with what you learned back in geometry. So because there are some very close similarities between how we're going to set up the integrand of our calculus problems or expressions with some of these examples I have up here, specifically the volume of this cylinder. And we're not going to be redoing this question necessarily through this example, but I'll use it in my lesson a little bit later. We may not actually completely rework it, but here we've got a prism whose bases are right triangles. And let's say that we have a prism. This is a right isosceles triangle that is forming the bases. And let's say that each leg here is equal to 3, and the height of this prism, let's say, is 5. I don't want any numbers yet. In general, how do we find the volume of this prism? Can you be a little bit more specific, a little bit even more generic than that, more general than that? No matter what, that right angle's in the wrong spot. No matter what prism I draw, no matter what the shape is, as long as it's a prism, as long as the two bases are the same shape and the same size, and, okay, it doesn't look too bad. What is the most general formula for finding the volume of a prism? Area of the base times the height. Okay, that's what I want to focus on. So for this particular prism, it's once again going to be the volume is equal to the area of the base times the height. So that volume, and this is the answer that it actually gave me. It's 1/2, let's say, in terms of the actual base of the prism, we have, again, a right triangle that's isosceles, so the two legs are going to be the same length. So the area of that base is going to be 1/2 the length of one of the legs, and one of our legs is 3, squared, times the height, which we've set to be 5. And we've got 3 squared is 9. 9 times 5 is 45. So we have a volume that, I meant to just do the base in red. We have a volume that is 45, right? 9 times 5 is 45. I'm early in the morning. Over 2 cubic units. Last example from the old days, but this time not very old. Whether you want to think of it as 4.3 and 4 when we get introduced to the definition of a definite integral, or our review of finding area between curves, which is literally the last section. We want to, this will seem like a silly example, and it kind of arguably is. Yeah, let's just do a really silly example. So we've got the line of y equals 3, another line of x is equal to 4. How do we find the area bound between the x-axis, the y-axis, and the two functions of y is equal to 3 and x is equal to 4? How do we find that area? Common geometric region. It's a rectangle. This area is going to be equal to just a base of 4 times a height of 3, and we get 12 square units. Cool? So all old stuff. Now, what would this have looked like? How would we have found the area under the curve of y equals 3 and the x-axis between the value of 0 and 4? How would we find that area using calculus? Okay, basically, how do we walk through this doing a definition of a definite integral, or using a definite integral? But I just said out loud actually what I want to review today as a foundation of this lesson, which is to say that yes, we're finding volumes of solids, but today's work is still going to have a foundation using the definition of a integral. Now, I could easily teach this lesson without reminding you of what the definition of a definite integral is, but we are, now 2.5 months away from the AP exams, and, it's a pretty important definition. It's literally the foundation of half of all calculus. You have to know this definition if you want to, maybe answer some questions about it specifically. Coming up here pretty soon. And I'm hoping that recalling this will help make all this stuff make sense, of course, as well. We have the limit as n approaches infinity of the summation where I starts at 1 and goes to n of f of c sub I times delta x, and c sub I is going to be equal to a plus whatever delta x happens to be times I for a right Riemann sum. That right Riemann sum, the upper right-hand corner of, this was back when we were in chapter 4 and we were trying to find area under curves between a couple of values of a and b. And there's lots of different Riemann sums. There's trapezoidal Riemann sums, which we learn and we'll relearn. There was rectangular Riemann sums, which is what I want to recall for this lesson. You can even do Riemann sums using parabolic curves, which we did not learn. But with a right Riemann sum, you would be drawing some, a certain number of subdivisions of rectangles, and we'd be adding the area of those rectangles to estimate the area under the curve between a couple of values. And then it applied to lots of other things as well. So your c sub I are these values of x. There's an x value of a, an x value of a plus delta x times 1, an x value of a plus delta x times 2, and an x value which is a plus delta x times 3. So each of these subdivisions would be a delta x. And n, remember, is the number of rectangles. Well, some values of x that you plugged into your function were a plus delta x times I for a right Riemann sum, and a plus delta x times I minus 1 for a left Riemann sum. So yeah, abbreviated right and not left. I don't know why. Delta x was b, we were told that it was b minus a. That is the upper value of, in this case x, but we can't integrate along the y-axis. So this is a larger value of either x or y, and this is a smaller value of either x or y. It's the interval along either the x or y axis where you're trying to estimate, at least up until now, the area or the value of some function. Definite integrals don't always have to just give you area. But we have delta x is b minus a over n. And then that is equal to the definite integral from a to b of f of x dx. Right now in this section we're talking about volumes of solids and we are literally building off of finding areas between two curves. But definite integrals, what does a definite integral give you in general? Just a number. That number might be an amount of coffee you poured into a cup over a 20-second period. It might be Like we talked about, I think when we started 7.1, I reviewed integrating velocity as displacement and integrating the absolute value of velocity as total distance traveled. I mean, this number can represent all kinds of things, an amount of profit over time, a number of miles driven over 8 hours or something like that. But so at its core, when you integrate, when you do a definite integral with the rate of change, you get an amount of change. We are strictly talking about geometry right now, and so we're thinking about this definite integral from a to b of f of x dx as area. That's what we just finished. You find the antiderivative of f, you get a capital F, you have your upper limits of b and a, and then you plug them in. And you're probably now thinking we're 20 minutes into class and Mr. Tour hasn't done one single problem that involves volumes of solids, but we're getting there. We're really close. So let's start with this problem, okay? This silly little question where we wanted to find the area under this horizontal line between that function and the x-axis, okay? We know the answer is 12, but if we wanted to evaluate this with a definite integral, and we got straight lines everywhere, we could integrate with respect to the x or the y. Let's actually do the both. Let's be fun. Let's set up a bunch of vertical rectangles. Think about that Riemann sum. We're going to let the number of rectangles go to infinity and just evaluate the definite integral. But let's work with this line, y is equal to 3. And each time I make a subdivision of this region with a rectangle, I'm setting up a new delta x, right? And if, if 5 rectangles are good, then 10 rectangles will be better, and 20 rectangles will be even better, and 100 rectangles will be even better. Of course, we're going to get the same answer over and over again because, of course, this is a common geometric region. We start with some simple algebra and build up. But this area would be a definite integral. If we want to integrate with respect to x, we need our lower and upper limits to be values along the x-axis. Well, this region starts at 0, ends at 4, so we're doing a definite integral between 0 and 4. We're integrating the function 3. We're going to integrate with respect to x, so we get a 3x. Our upper limit is 4 and 0. Plug in the 4 after the 3. And oh my gosh, it's a shocker. We got 12 units again. 12 square units like we knew in the first place. Maybe just for fun. Woo, it's just so much fun. This question's really boring, but I promise you in the end, hopefully, and you can give me feedback when we're done if this was a waste of time or if you got something out of this. We could lay some representative rectangles down horizontally. And with this question, the way you do it, it makes absolutely no difference at all. Other questions, one way great and easy, one way miserable and really super freaking hard, if not impossible. So what if you want to lay down some Riemann sum, some representative rectangles with a bunch of little delta y's? That means you're setting up a definite integral. Your area is going to be a definite integral, and you're going to be integrating with respect to y. Now, everything is just vertical lines, so we're not going to actually see a letter in our integrand. But if we lay our representative rectangles horizontally, the little delta y, just like over here, let's back up a little bit now that I've erased all the red rectangles. In terms of area, there was a lot of ahas when I said this back in chapter 4. The function that sort of f of x gave you the height of the rectangles, and the dx or the delta x gave you sort of that base, or it gave you a width for base times height. Well, here, the delta y now is going to be our base, and we're going to find a height off of a function. Now, this is such a simple example, it's not going to really look like this, but we're going to have a function not in terms of x, but a function in terms of y. And we're going to be integrating not along the x-axis, but along the y-axis. So we're going to be integrating between 0 and 3, not 0 and 4, like when the rectangles were vertical. So we're going to have a lower limit of 0 and an upper limit of 3. And it's a y value. We're going to be choosing values of y, because we're integrating with respect to y, and getting a value of x. So at this value of y, y is 1. what's our distance? What's the length of these rectangles? What's the x value? 4. At this value of y of 2, what's our x value? 4 minus 0, which is 4. At the y value 3, what's our x value? X value 4 minus an x value of 0. I think I misspoke earlier. But that's an x value 4 minus an x value of 0. 4 minus 0. 4 minus 0. No matter what the value of y is, the x value is 4. And of course, we get a 4x. Look, I bored David to death. His head's already on the table. Upper limit of 3 and a lower limit of 0. Plug those in. That should be a 4y, not a 4x. There you go. We have a 4y. We plug in the upper limit of 3. We have 4 times 3 minus 4 times 0. And oh my gosh, for this particular question, and with all questions, really, it's just a matter of how easy or hard is it, how hard is it to work out. We integrate along the x-axis with a bunch of little delta x's. We got a value of 12. We integrate along the y-axis. We got a value of 12. Different function, different limits. Different function, different limits. Same answer. Most of the time, you're not going to be able to easily integrate in both directions. OK, we good? So we have seen this definition of a definite integral for a long time now give us lots of different numerical numbers that mean many, many different things. But in terms of area, we've seen this definite integral give us area between curves. Now it's going to give us volume. Okay? This f of x is not necessarily just a function of height. It's a function that gives something. So now what we're going to do is we're going to reduce some of these geometry problems. They're still going to be rather basic, not quite as basic as this area problem. But let's say that I want to evaluate example number 1, again, with calculus. So let's call this, I don't know what example it would be by now, I guess example number 5. Or we're going to redo example number 1. We're going to lay this, so we're going to take the region bound between y is equal to 2, x is equal to 9, and we are going to take the region bound between these two curves in the x-axis in quadrant 1, and we're going to revolve them around about the line y is equal to 0. So we're going to take this area. This is why 7(2) follows 7(1). We're taking areas in a region bound by a couple of functions, if not more, and revolve them around an axis of rotation. Now, when things spin, what shape do you get? A circle. So this region is going to get spun around an axis and create, I know this will be very shocking, but it is going to create what? A cylinder. So we're going to have, and what's going to happen is this is going to look like a roll of quarters. Okay, think about a roll of quarters that with a paper sleeve that you can see through. You're going to have inside here, and kind of going back to, again, this idea of these representative rectangles that we had in chapter 4. When you take this representative rectangle and you spin it around a circle, you're going to get like a little tiny cylinder, like a coin. And you have a quarter and 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 a quarter, and you take all those quarters and you start stacking them up, and you just get a taller and taller and taller, a longer and longer and longer cylinder. And that's going to be a bunch of little delta x's, at least the way I've set up the diagram. Okay? And if I want to look at this as one cylinder that is cut up into just a whole stack of small little cylinders, like we did with our area problems back in chapter 4, where I said, what's the area of this region? I don't know. Well, let's cut it up into 3 rectangles. Now let's cut it up into 5 rectangles. Now let's cut it up into 10 rectangles. And every time we did that, these little pieces of these little areas that we missed got smaller and smaller and smaller and smaller. We're going to find the volumes of all those little teeny tiny disks and just add them up with calculus. We're going to let the number not number of rectangles like we did in chapter 4, but n is going to be now the number of little tiny disks that we're adding, cross sections that we're adding. And when we set up our definite integral, because we have rectangles that are perpendicular, all the representative rectangles will always be perpendicular to the axis of rotation. And the axis of rotation is right here. All the representative rectangles that are creating all those little delta x's, which then spin and make all those little disks, those representative rectangles that are spinning, making disks, are always perpendicular to the axis of rotation. So we're going to be then integrating, making some integral with respect to x. And we're going to integrate between two x values. Well, in this case, it's going to be between 0 and 9. And there'll be a function here. Now in chapter 4, like that silly little example I just erased, when I said, hey, look, Riemann sums is nothing more than the base of a rectangle times its height. Well, now this function's not going to give us a one-dimensional measurement. It's going to give us a two-dimensional measurement. The integrand of all of our problems today is going to be set up to be an area formula. And I'm going to say, I'm going to call it not the area of the base, but the area of the cross section. So when you go back to geometry and you're like, what's the volume of a prism? It's area of the base times the height. The area of the base, the area of the cross section, that is your integrand. That's going to be your f of x, your f of c sub I. And your height is either going to be a delta x or a delta y. I'm now finished with this lesson. I mean, we have a lot of examples to go through, but if I just made a little aha moment for you, that's the lesson. That's all we're doing. We're finding volume of prisms like we did in geometry. So what's the area of something spinning? What's the area of a circle? Pi r squared. Pi r squared. Now, what I want you to recall is there's going to be, for this particular problem, because the cross sections are circles, it's going to be pi times some kind of radius squared. Our radius is, every time I draw one of these rectangles, I'm actually drawing a radius. And if you're drawing vertical lines, how do you find the length of a vertical line? And you will have vertical lines when you're integrating with respect to x. How do you find the length of a vertical line? How do you find the length between two curves when you're trying to find the area? Big Y minus little y. And so this radius is going to be a big Y minus a little y, which is going to be kind of really seemingly stupid for this problem because it's just a horizontal line. This line segment is calculated. Now, for this problem, it doesn't change, but for many more it will. This radius, this line segment that's getting spun to make a circle is big Y minus little y. The big Y is at y equals 2. The little y is at y equals 0. Okay, so we have pi is a constant, so we can move it out front. Arguably, we could move all of out front because it's all a constant, but I'm going to go ahead and just move the pi out front. We can move the pi out front. We have pi times the definite integral between 0 and 9. 2 squared is 4 dx. Integrate 4 with respect to x. Now we have pi times 4x with a upper limit. I should be using brackets, not parentheses. We have pi times 4x with an upper limit of 9, a lower limit of 0. We have pi times 4 times 9 minus 4 times 0. And oh my goodness, I managed to do my math correctly this early in the morning. We once again have volume like we knew in the first place from basic geometry of 36 pi units cubed. The calculus matches the geometry formula. Good? Okay, let's step it up a little bit. Can I erase this? So now, for our sixth example, let's take a look at the cone. I want the volume of the solid formed by taking the region formed by the line. So the volume of the solid formed by taking the region bounded by y is equal to 2 over 9x. X is equal to, any guesses? 9 in region 1. And we're going to take this region and we are going to rotate it about the line one more time. Volume of solid bound by these two functions, rotated about the line y equals 0. Now, so this is our axis of rotation. And when we spin this, we're going to get a cone that, obviously, hopefully obvious, looks something like that. Our axis of rotation is once again a horizontal line, which means that we have a bunch of little delta x's that are perpendicular to that axis of rotation. And we're going to take all of these axes, all these representative rectangles, and we're going to rotate them about, again, that line of y is equal to 0. And so we're going to basically be finding the volume of a solid. Again, that's a bunch of stacked coins. But this time, the radius of the coins is going to be changing. That's what we're finding the volume of. This is not, the sides of this red and white plastic figure that some people keep playing with is actually formed by a parabolic curve. But this is kind of effectively what we're finding the volume of, with a bunch of little coins. Now, when the sides are parabolas and cubic functions and sine waves and stuff like that, calculus is 100% required. This question, calculus, we already did this problem. We know the answer is 12 pi cubic units, but I'm just trying to tie the calculus with the old stuff, make you see that it's the same thing. So let's see if it does come out to be the same. These are a bunch of little delta what? X's, which means we are integrating with respect to x. So we're going to find volume is equal to some definite integral from an x value of 0 to an x value of 9. And what is the integrand going to be? An area formula. And we are going to be integrating with respect to x. So we need an area formula that has what independent variable? X. This is technically called volume of solids using disk method. And for years and years and years, and shall make sure we get to it before the end of the period, I taught this with 3 different formulas. The disk method, the washer method, and the non-rotating solid method. And I just thought that the non-rotating solids was so freaking complicated. It was so hard to get my head wrapped around, until I finally realized, oh, these are all just area formulas. It's not really 3 methods. It's just the integrand is an area formula, period. Which, if you remember that alone, will make some of your AP questions really, really easy. So how do you find the area of what's this cross section? How do you find the area of a circle? Pi r squared. So it's pi times some radius squared. Well, the radiuses are a bunch of vertical line segments. Why vertical? Because you're cutting perpendicular to the axis of rotation. And so you're just moving in a vertical line. How do you find the distance of a vertical line? It's the big Y minus the little y. So my big Y is defined by the line. Where do all these radiuses stop at? Where's this big Y at? All these big Y's are on the line. What's the equation of the line? 2 over 9x. So we have big Y, 2 over 9x minus, where is the little y at? It's not always going to be a constant, by the way, and it's not always going to be 0. So write the minus 0 even when you don't need to. So you get that pattern down. Big Y minus little y squared dx. Pi r squared. That's all we're freaking doing. Setting up integrands that are area formulas. Sometimes those area formulas are circles. So we have a pi, which is a constant. We're going to bring that out. We have 0 to 9. And I'm getting tired of this stuff being in my way. We got 2/9 x squared dx. We're going to clean that up a little bit. So we have pi times the definite integral between 0 and 9. 2 squared is 4. Now, I know what's coming, so play along with me for a minute. I'm not going to do 9 squared. 9 is 3 squared, yes? And that 3 squared is now being squared. So instead of writing 81, I'm going to do 3 to the 4th. X squared dx. This 4 over 3 to the 4th is a constant. To not deal with that over and over again, I'm going to move that out front with the pi. So we have 4 over 3 to the 4th pi. What's the integral of x squared? X cubed. We raise the power up by 1 and then you divide. So we have a multiplication of 1 over 3 or a division of 3. And an upper limit of 9 and a lower limit of 0. I'm going to bring the 1/3 out again. And 3 to the 4th times 3 is 3 to the 5th. So we have 4 over 3 to the 5th pi times 9 cubed minus 0 cubed. 9 is 3 squared. And 3 squared to the 3rd power, 3 squared to the 3rd, nice, is 3 to the 6th. So we have 4 pi over 3 to the 5th times 3 to the 6th. Wonder why I wanted everything to be base 3. What's 3 to the 6th divided by 3 to the 5th? 3. What's 3 times 4? 12 pi units cubed. Same answer. Bam! Okay, one more pure geometry problem before we jump into like some stuff with curves in it. Once we get to the stuff with curves in it, it shouldn't be like basically at all different. Okay? And I'm also not going to do all the problems from the end because really the hard part of this lesson is the setup. We're going to revisit one more time these two problems, but this time we're going to have a cylinder with a hole cut in it. Okay, like a funnel. Only I've never seen a funnel where the sides go from paper thin to like solid at the bottom, but you know, bygones. So we want to find the volume of the solid formed by rotating the region bounded by x equals 0, y is equal to 2, and y is equal to 2/9 x. So here we have, I've already used blue, but I'll retrace this. We have y is equal to 2. We've got x, or y, excuse me, is equal to 2/9 x. X is equal to 0. Put that x and y axis back in there. And we are revolving around the line y equals 0. Okay, so the region that we are spinning is this region right here. So we're going to get a cone, we're going to get a cylinder that's got a cone-shaped sort of hole inside of it. When we make a cross section, if we take a knife and we run it right through, or take, maybe this is a piece of wood or plastic or something, we run it through a bandsaw, we cut this thing right through the middle. And we cut it right here. We are going to have basically 2 circles. One circle around the outside, right? That's the outside of the shape. And we're going to have another circle defined by the hole that's in the solid. And we're going to be finding the area of a circle with a hole in it. Now, this solid, the inside portion that I can reach my hand into, these sides are not straight. These sides are probably like maybe a hyperbola or parabola on both sides. Okay? But when we take this solid that's got a hole in it and we make one slice, that slice is a circle with a hole in it. How do you find the area? How do you find the area of a circle with a hole in it? How do you find an area of any region that has a portion somewhere within that region taken out? Area of the big circle minus the area of the little circle. So to find the area of this cross-section, okay, I've erased the definite integral notes, but our integrand is an area formula, and the height for the volume of a prism will be that dx or dx or dy, delta x or delta y. So how long is this large radius? How far is it from the, I know I'm asking the same question twice, I am aware of that. How long is the line, the radius, between the axis of rotation and the outside of that circle? And set it up as a subtraction even if it's an obvious answer. That is a vertical line segment between and the distance is measured between the outside of the region, the outside of the circle, and the axis of rotation. Big Y minus little y. 2 minus 0. So this radius is 2 minus 0. Now, there is a red circle in here. Okay, there's a hole in this cross section that has its own radius. Now, the distance between the function defining the edge of the sort of cone, the outside of the circle that you're taking out, this is the region that we're about to, this is the area that we're trying to set up a formula for, that's there in green. Okay, this radius is going to be changing. That radius, oh, getting a little longer, oh, getting a little smaller, getting way longer, and way longer. So I pick a value of x, and there'll be a different vertical length. How do you find a vertical line segment length? Big Y minus little y. How do you find a vertical length? Big Y minus little y, and you subtract the difference. So where are these big Y values at? Or on? They're on the, why is nobody talking to me? Where are all these dots at? On the line. Either say on the line or on 2 over 9x. So this little radius right here, which is variable, is found by doing big Y minus little y, big Y, little y, big Y, little y, big Y, little y. Big Y is the line, little y is the axis of rotation y value. And how do you find the area of a circle with a hole in it? Olivia, one more time. So it's the area of the big circle. It's pi times 2 minus 0 squared minus the area of the small circle, which is pi times big Y, 2 over 9x squared, pi r squared, area of the purple circle, pi r squared minus 0, pi times 2 over 9x minus 0 squared, area of the big circle minus the area of the small circle. Now you're going to do that over and over and over and over and over again and have a stack of cylinders that you're just finding the volume of. Okay, a stack of these cylinders that with holes in them that you're finding the area of. And we're integrating all of these representative rectangles are perpendicular to the axis of rotation. So these are a bunch of little delta x's, so we are integrating with respect to x. So we've got a dx out here. We're integrating with respect to x, so we're going, that volume is going to be from the definite integral between 0 and, once again, 9. of pi times 2 squared. Let me do this one more thing too. These two terms, what do they both have in common? Pi. So let's take that constant and move it out. Okay, both of these terms have a constant factor of pi. So let's factor the pi out and put it out in front of the integrand. And then we have pi times a definite integral between 0 and 9 of 2 squared, which is 4, minus, I'm going to go ahead and do all that base of 3 stuff again. 2 squared is 4. 9 is, just because I know it's coming up, I wouldn't normally do this, but 9 is 3 squared. So 3 to the 4th, and then x squared dx. So we have pi times the definite integral between 0 and 9. What's the integral of 4 with respect to x? 4x. Minus 4 over 3 to the 4th. What's the integral of x squared? X cubed. And then you're dividing by that increased power, you're dividing by 3, so times 1/3. What's wrong with my notation? I just integrated and kept my integral symbol. I yell at you all sometimes for doing that. Don't do that. I need those brackets with the upper limit of 9 and 0. So now we got pi times 4 times 9, so 4 times 9, minus 4 over 3 to the 5th, 9 cubed, but 9 cubed, I don't know what 9 times 9 times 9 is, but I know 9 is 3 squared. So 3 squared to the 3rd is 3 to the 6th. And I'm going to take advantage of that because I have a base of 3 in the denominator right here. I have a 3 to the 5th. And then minus 4 times 0 is 0, and anything times 0 is once again 0. So we have pi times 9 times 4 is 36, minus 3 to the 6th divided by 3 to the 5th is 3, times 4 is 12. So we have 36 pi minus 12 pi. What was the volume of the cylinder? 36 pi. What was the volume of the cone? 12 pi. Oh my gosh, the calculus matches the geometry. 24 pi cubic units. Now, if you go to your textbook and you look at the volume of a solid using a disk method, now that I've erased my examples as I go, the volume of a solid using the disk method is pi times a definite integral from a to b of capital R of x dx, or it'll be an ry dy squared, because it's pi r squared. And the quote-unquote washer method is pi times a definite integral between a and b of capital R of x squared minus little r of x squared dx, which is exactly what we did. What could we do with this pi? Move it out. And what was the 4? The outside radius squared. What was the 4 over 3 to the 4th x squared? The inside radius squared. Now, volumes of solids don't have to rotate. So we're going to find, for example, I didn't know what I'm on now. Find the volume of the solid whose base is defined by y is equal to 3, x is equal to 5 in quadrant 1. Each cross section is cut perpendicular to the x-axis and is an isosceles right triangle with a leg as its base. Can't imagine where I got this example from. So we have an x-axis, a y-axis. We have the line of y is equal to 3. So 1, 2, 3. We have x is equal to 5. And every time I make a cut perpendicular to the x-axis, so I'm slicing perpendicular to the x-axis, which means we have, and if I try to make these three-dimensionals, it's going to really look like garbage. But we're going to make a slice, and we're going to make a slice, and a slice, and a slice, and a slice, which means we have a bunch of little delta x's, which means we are integrating with respect to what? The x-axis. And every cross-section is a isosceles right triangle where one of the legs is the base. So we're just basically laying this prism down on its side, one of the sides. And so it's oriented like this. God, do I dare try and draw this? Can you see that? And it's like a, you know, half a sandwich. Okay, we took a loaf of bread, we sliced it, and then we cut it along the diagonal. So every cross-section is a isosceles right triangle. This is the base right there. That's the base. And this is the height. I know I got red all over the place, but that's the height. And then you have the hypotenuse. How do you find the area of that isosceles right triangle? 1/2 the base times the height. But it's isosceles, so the base and height are what? The same. So that cross-section, that area, is 1/2 the base, one of those legs, squared. Now we know the volume of this prism is 45 over 2 square units. We already figured that out with geometry. But let's see what it looks like with calculus. That's going to be, the volume is going to be the definite integral between 0 and 5 of 1/2 the base, big Y minus little y. What's a big Y at? 3. Where's it stopping at? Y equals 0. So 3 minus 0 squared dx. So that's going to be 1/2 out front, definite integral, 0 to 5. 3 squared is 9. Integrating with respect to x. That gives us 1/2 times 9x with an upper limit of 5 and a lower limit of 0. That's 1/2 times 9 times 5 minus 9 times 0, which is 45 over 2 cubic units. Wow, same answer. Can we see it? We just did volume by disk, washer, and non-rotating solids. We're going to have to do a lot more examples in the next class together, which is chapter 5, and I'm going to do more examples over the next like 20 minutes. But does that make sense? Okay, good. Let's do a very classic textbook problem. We're not going to do the actual integration and plug into the numbers because I want to talk about setup of problems. How do you find the volume of a solid? It's a definite integral from A to B of an area formula, and then it's either going to be dx or dy. Here we go. For another example, we're going to do the same functions with 4 different problems. We've got find the solid, find the volume of the solid bounded by these functions rotated about some axis. Function number 1, y is equal to square root of x. Function number 2, y is equal to 0. Function number 3, x is equal to 3. So we've got a square root function, a y equals 0 function, an x equals 3 function. This is the region. And we are going to revolve this about the x-axis. Or in other words, about y is equal to 0. If I take this region and I rotate it about the line y is equal to 0, will there be a hole in the solid? If the region touches the axis of rotation throughout the entire domain of interest, the answer is no. This solid will have no hole in it. So when you take this solid and you rotate it, I'm going to take a little bit of time to do this, but if you kill yourself trying to see what the shape of all these solids look like, you're wasting your time. You don't have to know what the solid looks like. But this solid is going to look like sort of like the nose cone of a propeller plane, maybe a cup, glass, whatever. But we're going to find the volume of all these little individual disks and add them up. Okay, I'm not going to draw the disks this time. But there is a radius, okay? If we revolve around a horizontal line, our representative rectangles are going to be perpendicular. Okay, your rectangles are always perpendicular to the axis of rotation, and that's a bunch of little delta what? Change along the x-axis or y-axis? X-axis. And every single one of these radiuses are going to be different. You pick an x, you get a radius. You pick an x, you get a radius. You pick an x, you get a different radius. You pick an x, you get a different radius. So the radius is not 3. That's just the radius at the base. The radius is always changing. So when things are spinning, what's your area formula? It's a circle. I guess I asked a bad question. When things are spinning, your shape is a circle and your formula is pi r squared. The first 4 examples are going to be all circles. So this volume is going to be pi times the definite integral between, what's this x value? What's that x value? So it's going to be pi times the definite integral between 0 and 3 of pi r squared. How long is this radius? What's the big Y? Square root of x. What's the little y? 0. So it's going to be the square root of x minus 0. Big Y minus little y. Write that even when it's 0. Okay? And we're going to integrate with respect to x. We're not going to finish this. This is pi times 0 to 3. The square root of x squared is x dx. When you finish that, the answer is going to be something that you'll finish in your homework. Okay? It's 9 pi over 2. Okay? That should be your answer if you do it correctly. Okay. Next example. Same 3 functions. Y is equal to square root of x. Y is equal to 0. X is equal to 3. Okay? So we've got square root function, y equals 0 function, x equals 3 function. Here's our region. And we want to rotate this region about the line x is equal to 3. So this now is our axis of rotation. Representative rectangles are perpendicular to axis of rotation. So these are our representative rectangles. What do we have? A bunch of little delta what? Y's. Which means we're integrating with respect to y. So volume is going to be some kind of definite integral with respect to y, not x. Well, if we're integrating with respect to y, all of our functions need to be in terms of not x, but y. So how do I get this x in terms of y? How do we solve this for x? Get rid of the square root, square both sides. So this is x is equal to y squared, which I guess I should leave in black. If we're integrating with respect to y. What do these numerical values represent? Values of x or values of y? Y. So where's the small y at? 0. Where's the big y end? If x is the square root, if x is 3, then this coordinate right there is 3 square root of 3. So we're integrating between 0, and I think I heard a bunch of you say that. Nice job. 0 and square root of 3. If we move horizontally, what's changing? X or y? The x. Where are the big x's at? To the right. Where are the small x's at? To the left. So this is the big X. This is the little x. What's the big X? Where all these lines start? At the x value of 3, which I guess I obliterated. So your big X is 3. And where are all these little x's? They're on this black curve, which is x is y squared. Big X, 3. Little x, y squared. Now things are spinning. What's the area? What's the shape when things spin? What's the area of a circle? Pi r squared. So the next line is pi times the definite integral between 0 and square root of 3 of 9 minus 6y squared plus y to the 4th dy, and you need to finish that. Let's just do one more. What about, and we're moving on to something else. What about we have, by something else, it's still another volume question. Okay, same thing. Y is equal to the square root of x. Y is equal to 0. X is equal to 3. We're revolving this about the, do you want to use an axis line or another random line? Random line? Okay. So we're going to rotate about x is equal to 5. Y is equal to the square root of x. Y is equal to 0. X is equal to 3. This coordinate we now know is 3 square root of 3. This is the region. This is a rotation line. So this is going to be like a cone washer. If you've ever seen any kind of like or done any kind of plumbing, it's going to be a hole in it, and it's going to be sort of like a domed, it looks like an eyeball. But it's going to be, it's basically like a lot of soft rubber washers for plumbing. It has this like dome shape through it with a hole that usually like a copper pipe or something like that slides through. Okay, and we're going to find the volume of that region. This region is not touching the axis of rotation. It doesn't matter if the axis of rotation touches at one little teeny tiny point, okay, whatever. But if you have any kind of region or any area where the region doesn't touch the axis of rotation, you're going to be finding the area of two circles subtracted, or using the quote-unquote washer method. So we need to set up an integrand. When we slice this through, okay, so I'm going to come through and make a slice right here. You're going to need to set up a definite integral as this thing spins. Okay, the outside function's in black. You need to find the area of the black circle and subtract it with the area, this inside line is red, and subtract the area of the red circle. And then ultimately find the area of that circle with a hole in it. So how do you find the area of a black circle, of this black circle? Pi r squared. So it's pi times how long is the radius of the black circle, which is not constant. Did I draw a horizontal or vertical line? Horizontal. So big X minus little x. Big X minus the little x. What's the big X? 5. That's the axis of rotation. Big X minus little x. Oh, okay, now hold on a second. Am I going to do y is equal to square root of x, or am I going to do, that's a bunch of little delta y's. So we need x is y squared. So big X, 5, little x on the parabola, x is y squared. Big X minus little x, pi r squared. And then minus, let's find the area of this red circle. How do you find the area of a circle? Pi r squared. How long is that radius? Nope, I don't want to hear that. Big X minus little x. 5 minus 2. 5 minus 3. Happens to be 2. And we are integrating with respect to what again? Y. So this volume is a definite integral between the small y of 0, large y of square root of 3, pi r squared minus pi r squared dy. These two terms both have pi's. The pi can come out. 0 to square root of 3. I'm not going to finish this. This is going to be 5 minus y squared squared minus 2 squared dy. If you do finish it, when you do finish it, never mind, I don't have the numerical answer, just figure it out.